Hey everybody, your Friendly Math Tutor here with another lecture video. Today we're going to finish Unit 9, so this is Part 2, and today we're going to focus only on polar. So check out the last video where we went with parametric and vectors because they went really well together. We'll refer to a little bit of that, but today we're going to just dive into everything polar that could be on the AP Calc. Unit 9 is only for BC. As always, make sure you like this video, subscribe to our channel, subscribe to our Patreon, check out our TikTok, Instagram, and Facebook, where we post videos that will be AP problems related to these topics. So let's dive in. So before we do any calculus with polar, let's just do a quick review of exactly what polar coordinates are. So if we think about the rectangular coordinate plane, if you have a point that's on the plane, the way that we get there is through going along the x-axis some number of units, left or right, and then going in the y direction up or down. So basically, if you start at the origin and you go over x and up y, that'll get you to some point that we call xy. All right, so that is how rectangular coordinates work. You've been working with that system for many years now. You're just going left, right, up, down to get to any point. What polar does is say, okay, well, what if there's a different way to get to that same point? Instead of going over x and up y, what if I went directly to the point, and I call that r, and I went on some angle made with the x-axis that we call theta. So we have this new way to get to the same point by going directly there on an angle as opposed to going over and up. And it leads to four formulas that you need to know to be able to go back and forth. So those formulas are just Pythagorean theorem. So x squared plus y squared equals r squared. So this is if you have x and y and you want to find r. That's how you're going to do that. And then theta is if you do the tangent of theta, that's going to equal y over x. So again, if you have y and x, you can easily find theta by doing the tan inverse of y over x. The other equations that are super important would be, let's say I took the cosine of theta. Well, that would be x over r. But instead of putting over r, I can move the r over here. So I get x equals r cosine theta. And likewise, if I wanted to think of what the sine of theta was, the sine of theta would be y over r. So that's y, and then I can bring the r over here. So these are our four equations that we're going to use to relate rectangular to polar. So with that being said, let's take a look at what derivatives look like in polar form. So in polar form, they can ask you two types of derivatives. One of them is just dr d theta. And all that is literally just taking the derivative of this, where r is like the y and theta is like the x, like normally dy dx, just dr d theta. So the derivative of 6 sine 3 theta is going to be, well, this is cosine 3 theta times 3, so it's going to be 18 cosine 3 theta. It's important to understand what that is telling us. So let's say we had to evaluate that at theta equals pi over 4. That would just be 18 cosine 3 pi over 4. Cosine of 3 pi over 4 is negative root 2 over 2, so that's negative 9 root 2. And what that means, so what dr d theta actually means, is the rate at which r is changing with respect to theta. So at a particular theta, it's telling us the rate at which the distance to the origin, r, is the distance to the origin. So if they want to know the rate at which the distance to the origin is changing with respect to the angle, you're going to find dr d theta. And in this case, it would just be negative 9 root 2. So then the other way is if they want you to find dy dx. So now that's different. That's asking us, based off some polar curve, which we're about to get to, that would be on top of the, again, they're not different coordinate planes. It's the same coordinate plane, just two different ways to move around on that coordinate plane. Think of it, you got the rectangular coordinate plane you've always worked with, and now you're putting the polar on top of that and just getting places in a different way. So you could still make a curve that could be written in rectangular or polar. And if you find dr d theta, that's the rate at which the length to the origin is changing. But you could find dy dx, which still gives you the slope of the tangent line in terms of on the original coordinate plane, right? Slope, rise over run. But in order to do that, we've really got to look at this as a parametric concept, because polar coordinates are really just parametric, like this. X is always r cosine theta, and y is always r sine theta. So if we really want to find dy dx, we've really got to find dy d theta over dx d theta. This is almost exactly the way, if you look at the last video of how we did it, it is exactly the way that we did it in parametric. It's just theta is now our parameter, and as opposed to it was t before. So what we need is we just need equations, x equals and y equals. Well, x is always r cosine theta, and r is 6 sine 3 theta. So what this really means is x is 6 sine 3 theta, that's the r, times another cosine theta. Y is 6 sine 3 theta, again, r, this r, which is the r given in this problem, times another sine theta, because it's r sine theta. All right, so basically you have r in both of these. X is always r cosine theta, y is always r sine theta. And if we want to find dy dx now, which is the slope of the tangent line, or at least an equation for the slope of the tangent line at a given theta, we are just going to find these two derivatives. So we're going to do dy d theta first. Here we're going to use the product rule. So the derivative of 6 sine 3 theta is 18 cosine 3 theta times sine theta plus 6 sine 3 theta times cosine theta. So I use a little product rule there. That gives me the derivative of this. On the bottom, I need dx d theta. I'm going to do a similar thing. Derivative of 6 sine 3 theta we see is 18 cosine 3 theta times this time cosine theta. This time it's going to be minus because the derivative of cosine is negative sine. So it'll be negative 6 sine 3 theta sine theta. We could evaluate that at any theta, and that specific value would simply just be the slope of the tangent line. Whereas in this problem, the specific value that we got represented the rate at which the distance from the origin was changing. All right, so one more time, dr d theta is the rate at which the distance from the origin is changing with respect to theta. And this dy dx is just the slope of the tangent line of this polar curve at a specific value. All right, again, we could plug in here. This is just would kind of be a bunch of busy work and take a bunch of time, but we could just plug in for each theta and we could get an actual numerical value for slope, given any theta. Okay, let's move on to some more polar curves. All right, let's move on to areas of polar regions. So real quick, the formula. If you remember from pre-calc, the area of a sector was 1/2 r squared theta. That was just if you had to find the area of just a sector of a circle. Now, we're not going to go through a full proof. Again, the point of these videos is just to kind of help you prepare for the AP test. There's plenty of other videos if you want to just go through the actual proof of this. But it's good for you to just understand at least slightly where it comes from, just so if you already know this formula, then the formula that I'm about to give you is going to make a little bit more sense. So this leads to, if we want to find the area of a polar region, and we'll talk more when we actually sketch out these curves, but like you're basically, your theta is changing and it's moving this way, and you're sweeping out an area, and that area is what we're essentially finding. So instead of area under the curve, it's like an area that's swept out. So it's more related to the area of a sector. It's actually like these infinite number of little sectors that are changing by d theta. And what that does is this ends up becoming the formula, the integral from a to b, and ends up being the half. This half is out front. It's r squared, and the theta that's changing is what just becomes d theta. So this is our formula. So we can't simply just integrate the way we were able to in rectangular. We do need to use this formula to integrate. And most of the stuff that we do is going to be calculator problems, so we're not going to really talk about the actual integrals. The whole key here is how to set them up. That typically is the hardest part. So if we have to find the area of one petal here, let's just go over really quickly. This is a rose curve when it's of this form, a sine n theta. When this is even, there is double the number of petals. So there are 4 petals, and its sine curve is going to, the first petal is going to be just like in the first quadrant. There will be 4 other petals here. Not that we need them. We're really only looking at the first petal, all right? And the way we kind of do this is the key to this. So we're looking for the area of just one petal. The key to these problems, the thing that students have the most number of questions with is, what are the limits of integration? So you want to think of this petal kind of, we're at the origin. When are we at the origin to start, all right? So we want to think about what would make this 0. Well, the sine of 0 is 0, so that's a good, a good place to start, because if I just plug in 0, I'm going to be at the origin. So that's a good place to start. Now, what's going to trace out this first petal is, when's the next time that I'm going to come back to the origin? So when's the next time that I'm going to be getting 0 as an answer? Well, the next time that sine is 0 after 0 is pi. But it's not pi. I want to know 2 times what value would give me pi, so that I'd be taking the sine of pi that would then give me 0. And that is going to be pi over 2. So pi over 2. If we think about this again, sine of 0 is 0. We're going to start to move this way with our theta. And as we move this way, we're going to start to trace out our petal. And we are going to return back here. The next time we return back here will be pi over 2. There's no other time in between that would give us 0. So this must sweep out the entire first petal. And then it's r squared. So I'm just going to square this. This ends up being 16 sine squared 2 theta, d theta. And I did that already in the calculator. That ends up being about 6.283, which looks like that's just like 2 pi. But again, I just did that in the calculator. So the key is to kind of know how to set this up and how you pick the limits of integration, right? So let's look at another example. Here we got an inner loop. So let's take a look at the graph. This is this form where it's a plus or minus b cosine theta, or you could insert sine theta there. That is going to be a limacon. And there are different types of limacons. One of them is a cardioid, another one is a dimpled limacon, and another one is a limacon that has an inner loop. So they're telling us here that it does have an inner loop, but if you didn't know that, what you want to do with all the limacons is just plot 4 points. So just substitute in 0. Cosine of 0 is 1. 1 plus 2 is 3. So in the 0 direction, my first point is 3 units away. Then plug in pi over 2. Pi over 2 is in this direction. Cosine of pi over 2 is 0. So we go 1 unit in that direction. Then substitute in pi. Cosine of pi is -1. 1 minus 2 is -1. So in the pi direction, I go back 1 unit, so that puts me here. Then in the 3 pi over 2 direction, that's 0 again, so I go 1 unit in that direction. So I end up with, let me think about that. Oh yeah, it comes through the origin twice. Okay. So that's what the inner loop looks like. So what we need to do is find the area of the inner loop. So once again, we have 1/2 integral r squared. So if it's just a single area, that part should be pretty easy, 1/2 r squared. The key is finding the bounds to which is going to sweep this out. So let's kind of trace this. When we plugged in 0, we got here. And then we plugged in pi over 2 and we were here. And then we plugged in pi and we ended up here. So that means we're coming this way. So here, this is the beginning of the inner loop. And then I loop, and then I end up back here. So similarly to the last problem, I'm trying to figure out, well, where did I hit 0 first? And then when did I hit 0 second? So I can do that by simply just setting this equal to 0. Subtract 1 divided by 2, so I get -1/2 equals cosine theta. Think about where cosine of theta equals -1/2. That is going to be at pi over 3 is where it's +1/2. So it's going to have to be in the second and third quadrant. So it's going to be 2 pi over 3 and 4 pi over 3. And that is our answers to the question that I asked. So we know at 2, so it hits here at pi over 2, and then it hits here at 2 pi over 3, goes to pi, then at 4 pi over 3, it goes there again. So we're sweeping out this area between 2 pi over 3 and 4 pi over 3. And again, that was one I just did in the calculator, and I got 0.544. I'll put it down here. So that is how you find the area of just a single region. Let's move on to areas of multiple polar regions. All right, let's move on to areas of multiple polar regions. So when we did this in rectangular, there was simply just the area between curves, and that was it, and it was the top one minus the bottom one, essentially. So we're going to see something similar, but we got really 2 different types of problems here when it's multiple polar regions. You're going to see some problems where it's going to be inside one polar curve, but outside the other one. And then you're going to see some where they could be the same type of problem, but you're going to have two intersecting polar curves, but they want the interior of both. And they're done in a slightly different way. So that's really what I want to go over. So let's first take a look at just a quick sketch of what these look like. 3 cosine theta, that is a circle along the positive x-axis with a diameter of 3. So it really helps to know your polar curves. All right, so that's 3 cosine theta, and 2 minus cosine theta is I believe it's a dimpled Lima sign. What we can do is, again, quickly sketch the 4 points. So plug in 0 and you get 2. Say 1, 2, 3. Plug in pi over 2 and, oh, whoops, my bad. Plug in 0 and you get 1. 2 minus 1 is 1. Plug in pi over 2 and you get 2. Plug in pi and you get 3. So 3 in this direction. Plug in 3 pi over 2 and you also get 2. So this is some kind of, it's like dimpled a little bit there. It's whatever. Doesn't really matter necessarily what it looks like, but it doesn't have the inner loop. It's not a cardioid. Cardioid would touch the origin or the pole. This is simply just, again, it's called either a dimpled or sometimes they call it a convex Lima sign. So we're looking for the area inside the circle, but outside the limit sign. So it's this area. Now notice what happens is we have two intersection points, right? And let me use a different color here. The R for each of these going like this, right? Or the, if you just look at the angle. So it's going to start at this angle, and it's going to sweep out to this angle. And if I just do that for the circle, that's going to give me the area of all of that. But it's going to count the area inside the limit sign. But then I can subtract out the area of the limit sign between the same two values. So this leads to a little bit tiny shortcut. I'm going to be subtracting two integrals. But those two integrals, which is going to be different when we get over to this example, are going to have the same limits of integration. So what I can do, and another cool thing that I can do, is notice that we have symmetry. So if I just do this, I'm going to start at 0 and go to this value, and then I can just double my answer because clearly this and this are the same. So let's do that. So let's do 2 times a half. I know 2 times a half is 1, but I want us to actually see that. It's going to be an integral from 0 to something, which we're going to find. Because again, I'm starting here instead of starting down here. And then it is, so what we end up with is instead of it being, so it's going to be 1/2, instead of it being r squared, it's going to be big R squared minus little r squared. And then d theta. All right, that's the same concept of like the big one minus the small one, but we're just putting them in one integral. Instead of it being 1/2 big R squared minus 1/2 little r squared, we're factoring out the 1/2. So big R is going to be the one that's further away. So the whole time that we're sweeping out this area, the circle is the one further away. So I'm going to put that first. So that's going to be 9 cosine squared theta minus the limit is the inner one. It's going to be 2 minus cosine theta squared d theta. And so the last piece of the puzzle is, well, where do they intersect? Well, they intersect when you just set them equal to each other. So 3 cosine theta equals 2 minus cosine theta. Add theta, we get 4 cosine theta equals 2. Divide by 4, cosine theta equals 1/2. We just saw in the last problem, cosine theta is 1/2 at pi over 3. So we're going to integrate from 0 to pi over 3. It turns out that this one would have been negative pi over 3, so you could have integrated from negative pi over 3 to pi over 3 and not doubled it, but that just kind of makes it a little bit easier. Again, I did this one. This one was about 5.196. Yeah. So that's how we do the area inside the bigger curve and then outside of the piece of the curve, that's inside of that other curve. So you're going to be subtracting them, and they're going to have the same limits of integration. Now let's look at one where it's common interior. This one gets a little bit more confusing. So let's take a look at the graph first. 4 sine theta is just like 3 cosine theta. It's a circle with diameter 4. But since it's sine theta, its diameter is along the positive y-axis. So we're going to get a circle something like that. And r equals 2 is a circle radius 2 that's centered at the origin. So we're going to have something like that. So the common interior is this. So the way we're going to look at this is going to, also we are going to use symmetry for this one also. So first of all, let's just cut this here. And we're going to double our answer. So we're only going to find the area of this region over here. And a key point is going to be this, whatever that intersection is. So actually, let's just find that right away. So for that one, we're going to get 2 equals 4 sine theta 1/2 equals sine theta, and that happens at at pi over 6. All right, and so the way that we're going to kind of look at this is notice that there's notice this red line, so going at the angle of pi over 6. That split, so everything before that is only between pi over 6 and this curve. So this circle, the circle above. And then after that, all of that area between pi over 6 and pi over 2 is only contained at r equals 2. So they're not like this one where there's an area that's included inside the other area. These areas are just completely separate from each other. It looks weird, but basically, let me outline it here. So this little area here is only, all of the r's are only being traced. The curved part is only this circle. So again, we're going to do 2 times 1/2. That integral is from starting at 0, sine of 0 is 0, and it's going around to pi over 6. And we are integrating this for sine theta, so that's 16 sine squared theta, d theta. All right, that area is this. Now I want to add it to this area. So this time we're adding areas. It's another 1/2. This time I'm starting at pi over 6. So I'm starting at pi over 6. And now I'm following this curve. Well, that curve that I'm following is the second circle. So see, the first one only followed the first circle, and the second one only followed the second one. So I have 2 completely separate areas that I'm now adding here. And that's going to pi over 2. And then it's the 2, well, 2 squared is 4, d theta. So again, I know that I could distribute the 2, and I just wanted us to see all of that. I didn't want to do that simplification because, again, the 2 is because I'm only finding this area plus this area, and then I'm doubling the whole thing because I'm just using symmetry. That's where this 2 comes from. And then so it's the area of the one plus the area of the other. That one ends up being 4.913. Which again is not really the important thing. The most important thing here is that when it's inside one curve and outside the other, that's when they're usually going to have the same limits, and you can just do the first the one that's further away squared minus the one that's closer squared. When it's the common interior, usually you'll make up that interior with there will be like a theta, a straight theta that cuts it, where on one side is only one curve and the other side is only the other curve. And you can get those by simply adding them together, but you won't be able to make it one integral because they will have different bounds. It'll be usually this bound will be here and here, all right? Okay, let's move on to our last topic. All right, let's move on to our last topic on arc length in polar coordinates. So we saw before that arc length was kind of like we had this like curve, and then we did all these little kind of like little Pythagorean theorem hypotenuses that like we summed them up along the curve. And this is basically just the Pythagorean theorem where this was 1 and this was f prime of x in rectangular. Then if we did the same thing in polar, this was x prime and that was y prime. Now I want to show you how to get the formula in polar. I might have said polar here, I mean parametric. We did x prime and y prime. Now I want to use parametric to get the polar. So if we think about in parametric, polar is parametric. Polar is just a specific parametric where x is always equal to r cosine theta and y is equal to r sine theta. And then let's say we do x prime. Well, x prime, if we think of r and cosine theta, they're separate functions. The derivative of r is r prime cosine theta minus r times sine theta. What I did there was the product rule, and the derivative of cosine is negative sine. Likewise, y prime is just r prime sine theta plus r cosine theta. So I'm just doing the product rule there. And then what it wants me to do in this formula is to square both of them. I'm going to take a little bit of a shortcut here. So x prime squared is going to be the first one squared, so r prime squared cosine squared theta. Then I'm going to do minus 2 of these multiplied together, so 2r prime r cosine theta sine theta, plus the last one squared, so that's r squared sine squared theta. Then I'm going to go down here and I'm going to do y prime squared. Well, y prime squared is just r prime squared sine squared theta. Then it's going to be plus 2r prime r sine theta cosine theta. Then finally, the last one squared is r squared cosine squared theta. And then it tells me to add them together. Well, something cool happens here. When we add them together, this and this, they cancel out. I end up with, well, if we look at this first one, r prime squared, or actually this, r prime squared cosine squared theta plus r prime squared sine squared theta, I can factor out the r prime squared, and I'll have sine squared plus cosine squared, which is just 1. So that's pretty much gone. And I can do the same thing here. I can factor out r squared, and I'm going to have sine squared plus cosine squared, and that's just 1. So essentially, this thing in here, when you do the parametric formula, but you use specifically polar, you end up with this. This part just becomes this part. So the formula for the for polar arc length is the integral between 2 theta values. I'm using a and b for all of these, but these are just 2 values. Like these are 2 x values, these are 2 t values, and these are going to be 2 theta values. And then as the square root, you'll usually see r squared first plus r prime. I'm going to write it like this. Instead of r prime, they write dr d theta squared d theta. So that is the formula. Not that you're going to remember this, but just like don't memorize this proof. I just wanted you to see kind of how simple it was, that if we just use parametric and then apply it to polar, it just generalizes to this formula. So now let's just use that formula. So we want the arc length of one petal of 2 cosine 2 theta. So the way that rose curves work with cosine is, and this works for sine, when n is even, double it, that's the number of petals, 4 petals. The first petal, and the only petal that we really care about, is for cosine. So we saw in our last example, sine, that first petal was like in the first quadrant. For cosine, it's always going to straddle the x-axis. So the petal in question here is going to look like this. We're going to use symmetry again. So if what we want to do is, remember, the cosine of 0 is 1. So we're really starting here, and then we start to make our way back. So if we just find that length, we can double it. So right away, we're going to double our integral. Now we got to find the bounds. Well, this part of the curve that we're starting at is 0, because again, cosine of 0 is 1, 1 times 2 is 2, so we're right here. So we're going to start at 0. Then we need to know the first time that we get back to 0. So we can just do 0 equals 2 cosine 2 theta, get rid of the 2. So we're basically saying the cosine of what is 0? Well, that's pi over 2. That's the first time cosine is 0, but we want to know what we double to get that, so that's going to be pi over 4. So if I go from 0 to pi over 4, that's going to be tracing out this arc. And then I'm just going to use the formula. It's the square root of r squared. Well, r squared is 4 cosine squared 2 theta plus dr d theta squared. Well, let's find dr d theta. So we're finding the derivative, but this time it's dr d theta, not the dy dx derivative of polar. So it's the actual dr d theta, so that's just a really straightforward, just what's the derivative of 2 cosine 2 theta, and that's negative 4 sine 2 theta. And if we square that, that's 16 sine squared 2 theta d theta. This is another one that I just did in the calculator, and that is approximately 3.14. And that's after we double it. I believe. You'll have to double check that at home. You'll have to double check that at home, but I'm almost positive that when I did multiply it by 2. So that should be, this number should represent the entire arc length, which is basically pi. So I'm pretty sure that's right. 1 petal on these is pi. Okay. All right, so that brings us to the end of Unit 9. So we've got 1 unit left, which is going to be 2 more videos on infinite sequences and series, which means we've only got a couple more weeks until the actual exam. So I hope we're finding these videos helpful. Check out our other videos on Patreon and worksheets. Check out videos on TikTok, Instagram, and Facebook. And have a wonderful day.